Hello everyone, welcome to this new video. In this video, we are going to talk about boundary conditions, which is again a very important topic to study the behavior of electromagnetic propagation in different media. So, we'll try to study the behavior of electric field and magnetic field at the boundary of two different medium, and after that we'll try to solve some numerical problems as well. So let us now move to the topic. So first of all, why we need to study boundary conditions? Basically, we study boundary conditions in terms of electric field and magnetic field to know the continuity or discontinuity of electric field or magnetic field at the boundary of two different medium. For example, I have an electromagnetic wave which is propagating like this. At this point, I have a boundary which is separating two different regions. For example, this side is having made up of air and this side is made up of, let us say, water. So this border is nothing but it is called the boundary of two different medium. Now at this boundary, what will be the behavior of electric field or magnetic field, that we will try to figure it out under the topic boundary conditions, because that will only give us the idea how my wave has changed from this region to this region. Okay, whether the orientation or the pattern of the wave remains same or it has changed. If it has changed, then how it has changed or to what extent it has changed. All these things will be answered if we know the boundary conditions, and based on that, if we try to find or analyze the behavior of electric and magnetic field. So in boundary condition, in terms of electric field, what we do is we basically focus on two terms or two components of electric field. One is called your tangential component. So one component is called tangential component or tangential part, and the other part is called normal component. This thing is also applicable for magnetic field also. While when we study the behavior of magnetic field across two different medium or the junction of two different medium, there also we represent magnetic field in terms of two components, the tangential component and the normal component. So basically what we can see is, or what we can say is, that this electric field can be represented as a sum of two components, that is the tangential component and the normal component. Okay, so now what is tangential component or what is normal component? It depends on the orientation of the surface. Let us say my surface is like this, it is aligned vertically, and this is the positioning, or this is the orientation of electric field. So now I can divide this electric field into two components. One is this horizontal component, and then this is the vertical component. Okay, now this horizontal component, which I am calling horizontal component, it is perpendicular to the surface. Okay, so this component I will call it as a normal component. So this will be nothing but my En vector, and this line, which perpendicular line, which is actually parallel to the surface, this is, I'll call it as a tangential component of the electric field. Okay, now again, let us say if the surface orientation has changed like this is the orientation of the surface. Okay, and my electric field is again like this. So again I can divide it into two components, horizontal and vertical component. Now in this case, this component, it is perpendicular to the surface, so this will be my normal component En, and this will be my tangential component Et. So this tangential component and normal component, it mainly depends on the orientation of the surface. Okay, and based on that we can define which component is tangential component and which component is normal component. Similarly, this is also applicable for magnetic field. A magnetic field can also be divided into two components, the tangential component and the normal component. This I am writing assuming that my surface orientation is like this, horizontal. Okay. Now, what will be the behavior of this tangential component and normal component of electric field at the boundary of two different medium that we will see. So let us say there are 2 points. This is point number 2 and then this is point number 1. Between point number 1 and 2 there exists a boundary which is differentiating or which is making a partition between medium 1 and medium 2. Now this medium 1, it is being represented by quantity called permittivity, which is epsilon 1, and the medium 2 is represented with permittivity with which has a value of epsilon 2. Okay, this epsilon is nothing but it is again equals to epsilon naught into epsilon r, where epsilon r is the relative permittivity. So for epsilon 2 it will be epsilon naught into epsilon r2, and for epsilon 1 it will be equals to epsilon into epsilon r1. Okay, so this epsilon 1 and this epsilon 2 will be something like this. Now let us say my wave is propagating from medium 1 to medium 2. In medium 1 the electric field is oriented like this. So this orientation of electric field I am calling it as E1 vector. After entering into E2, after entering into the medium 2, the orientation of electric field has changed to something like this. Randomly I am assuming that this is the new orientation of electric field, because most obviously the orientation of electric field 1 and 2 is going to be differ because the mediums are two different mediums. Okay, now this E1, it can be divided into, as I discussed, it can be divided into E1t, and it can, this component will be called as your E1n. Why I'm calling it as a tangential component and this one as a normal component? Because my surface orientation is kind of horizontal. Okay, so that's why this electric field 1, it can be divided into two components, E1t and E1n. So basically your E1 vector is nothing but it is sum of E1t vector plus E1n vector. And also this E2t vector can also be divided into E2t vector and E2n vector. So my E2 vector is nothing but it is E2t plus E2n. Now it can be proven that by doing mathematical analysis, I am not getting into that part, that the tangential component of electric field will remain continuous at the boundary of two different medium. That means E1t will be equals to E2t. The interpretation of this mathematical expression is that tangential component of electric field is continuous at the boundary of two different dielectric. Okay, now we all know that electric flux density D vector is nothing but it is epsilon into E vector. So this E1t, it can be written as D1t upon epsilon 1 and D2t upon epsilon 2. Okay, now since epsilon 1 and epsilon 2 are not equal, that means D1t will not be equals to D2t. So that means at the boundary of two different medium, they are discontinuous. Okay, so what we have learned from this particular slide is that the tangential component of electric field will be continuous at the junction of two different dielectric medium, and the tangential component of electric flux density will be discontinuous between the boundary of two different dielectric medium. Now, likewise, it can also be proven that d1n minus d2n will be equals to rho s, where rho s is nothing but surface charge density. Okay. So suppose this is the surface which is differentiating medium 2 and medium 1. So rho s is nothing but it is the surface charge density at the junction of two different medium. If there exists no surface charge at the junction of two different medium, then in that case d1n will be equals to d2n when rho s is equals to 0. Okay, so this is the condition of normal components of electric flux density. They are continuous at the junction of two different dielectric medium when there is no surface charge at the when there is no surface charge present at the junction or at the boundary between two different medium. Okay, now if we assume that my e1 vector is making an angle theta 1 with the normal line, if I draw a line, perpendicular line like this, and if my E2 vector is making an angle theta 2, so I can also prove that tan theta 1 divided by tan theta 2 will be equals to epsilon 1 by epsilon 2. So this is nothing but it is a form of expression which represents or which satisfies the law of refraction. Okay, so what we have learned from this boundary condition for electric field is that the tangential component of electric field is continuous at the boundary, and the normal component of of electric flux density is continuous at the boundary, provided the surface charge density is equals to 0. Similarly, we can prove that the normal component of electric field in medium 1 will not be equals to normal component of electric field in medium 2. And here in case of flux density, we can prove that d1t will not be equals to d2t. So these are some important formulas related to boundary condition of electric field between two different dielectric medium. Now, let us try to solve one numerical on boundary conditions for electric field. So the question is like this, that there is two semi-infinite homogeneous isotropic dielectric media which are separated by plane z equals to 0. So before solving this kind of problem, we need to understand the positioning of the plane which is separating two different media. Okay, so first I'll draw the three coordinate axes. So let us assume this is my z axis, this is my x axis, and this is my y axis. Now the question is saying that there exists one plane at z equals to 0 which is differentiating two different medium, or which is separating two different dielectric medium. One medium exists above z greater than 0, and the another medium exists below z less than 0. So what I can assume is this particular region, it represents my z greater than equals to 0, z greater than 0. Okay, so this region has a permittivity epsilon r1 equals to 4. Then this region, it represents my z less than 0, so this region has permittivity er2 equals to 3. So if we try to see this from the side view, let us say this is my x-axis, this is my z-axis, and this is my y-axis which is coming out of this page. Okay, so these are the positioning of my three axes. So it is saying that in z greater than equals to 0, that means in this portion exists my one dielectric medium which has a permittivity epsilon r1 equals to 4. And then in the z minus z less than 0 region, I have another dielectric medium which has a epsilon r2 equals to 3. So basically this is nothing but it is my plane which is differentiating the two different dielectric medium. Okay, now we need to understand from the given expression of electric field which one is the tangential component and which one is the normal component. So let us consider that it is given that E1 is given, so obviously E1 will exist in medium 1, so this is my E1. Okay, now if you see simply this E1, it can be divided into two components. This is my E1t and then this is my E1n. Now if you see the two vectors, this is the normal vector, this is the tangential vector. Normal vector is aligned along which direction? The normal vector is aligned along z direction. So my direction of normal vector is nothing but it is along the z axis. Okay, and my tangential vector E1t, it is nothing but it is along the xy plane. Okay, so this is the orientation of the two vectors which are contributing E1 vector. One is the normal component and tangential component. The normal component is aligned along z axis and the tangential component is aligned along xy axis. So what I can do is I can simply write E1t vector is nothing but it is my 5ax cap minus 2ay cap, and E1n is nothing but it is my 3az cap. Okay, otherwise we can also calculate the normal component in this way. The normal component E1n vector will be nothing but it is E1 vector dot which axis is perpendicular to the surface. If this is my surface, the axis which is perpendicular to the surface is z axis, so it will be nothing but it is my az cap or az vector. Okay, so this is how I can get the E1n vector. Now in previous slide I have mentioned that my E1 n vector will be nothing but it will be dot product of E1 dot az cap or az vector, whatever you call it. But if you look at this equation carefully, on the left hand side we have a vector quantity, on the right hand side we have a dot product. Now result of dot product always gives us a scalar value. Okay, so it is not so the dimensionality of this equation is not matched, so actually it will be E1 dot az into az cap. Okay, this az cap is nothing but it is the direction of E1 n vector, and this E1 dot az cap is nothing but it is the magnitude of this normal vector. Okay, so in this way we can calculate the normal vector. So ultimately, basically what we have done is, from the given expression of electric field, we have identified the tangential component and we have also identified the normal component. Okay, now our intention is to calculate E2 vector, and this E2 vector will be nothing but it will be equals to E2t vector plus E2n vector, sum of tangential component plus normal component. Now from the condition of boundary of two different medium in terms of electric field, we know that E2t is equals to E1t. So from that we can directly write that E2t will be nothing but my 5ax cap minus 2ay cap. Now the question is how to calculate E2n. So to calculate E2n, the formula is E2n is equals to D2n divided by epsilon 2. Okay, this is basic, very basic formula which correlates electric flux density with electric field intensity. Now this D2n, it can be written equals to as D1n from the boundary condition of electric flux density, normal component of electric flux density, and this epsilon 2, it can be written as epsilon into epsilon r2. Okay, then this D1n, it can be written as epsilon 1 into E1n vector. Okay, and here I'll write epsilon into epsilon r2. Then epsilon 1 can be written as epsilon 1 into epsilon r1 E1n vector whole divided by epsilon into epsilon r2. So this epsilon naught will get cancelled out. So what is left out with is epsilon r1 e1 n vector divided by epsilon r2. Now the value of epsilon r1, the value of epsilon r1 as given in the question is uh, it is given as your 4, and epsilon r2 value it is given as 3. Okay, so what I can get is my e2n vector is nothing but epsilon r1 by epsilon r2 into e1 and vector. Epsilon r1 is 4, epsilon r2 is 3, and epsilon 1 vector is nothing but it is 3az cap. So this 3 will get cancelled out. So what is left is 4az cap. So ultimately my e2 vector will be nothing but it will be 5ax minus 2ay plus 4az. So if E1 is given to us, we can calculate E2 by using boundary conditions, and vice versa. If E2 is given to us by using the boundary conditions, we can also calculate E1. Now, in previous example, we have seen that for solving numerical problems related to boundary value conditions, it is very essential that we first identify the positioning of the plane, and based on the position of the plane, which one will be the normal axis and which one will be the tangential axis, or which two axes will be the tangential. So if my axis orientation is like this, let us say this is my z-axis, this is my x-axis, this is my y-axis, and if my surface is oriented like this, okay, this orientation is called z-plane, or it is also called as your xy plane. Okay, so if my surface is oriented in xy plane or in z plane, in that case normal vector will be nothing but it will be my az vector. So tangential will be my xy plane or ax vector, ay vector. Okay, similarly, if the orientation of axis is like this, z, x and y, and if my surface is oriented like this, okay, so this kind of orientation is called x plane or yz plane. So in that case normal vector will be my ax cap, and tangential vector will be my ay and az plane. Okay, it will be represented it will be represented by a plane which is having ay cap and az cap. Similarly for y plane, the normal vector will be ay cap, and the tangential vector will lie in the ax az plane. Okay, so it is very important to identify the orientation of the plane which is differentiating the two dielectric medium. Okay, and based on the orientation of the plane which is differentiating the two medium, next important task will be to identify the direction of normal vector. So now let us try to solve one more similar kind of problem. So in this problem it is saying that first let me draw the three axes. This is my x-axis, this is my y-axis, and this will be my z-axis. So two dielectric medium extend infinitely and are joined along the yz plane. Okay, x equals to 0 interface, it has mentioned in the question, but sometimes it may not be mentioned. So it is what I want to focus is, I want to focus on this term yz plane. That means my plane which is separating the two dielectric medium, it lies on this axis like this. Correct? So this is the plane which is separating two different medium. This is one side, this is the other side. Now the side which is lying on the x greater than 0, that means this part, it is being called as your right half space, and the side which is existing in x less than 0, that means this side, it is called as your left half space in the question. Okay, and this region has a permittivity 4 epsilon naught, this region has a permittivity 3 epsilon naught. These informations are given in the question. And also E1 is nothing but it is my 5ax minus 2ay plus 3az cap. This is the value of E1. So our first task will be to find out the tangential component and normal component. Now if the surface is aligned along your yz plane, that means which axis is perpendicular to the surface? X-axis. So which vector will be the normal vector to the surface? It will be my ax cap. So ax cap is the unit vector which will be normal to the surface. Okay, so E1n vector will be nothing but it will be your E1 dot ax, and E1 will exist in the x direction only, so it is ax. So ultimately this will give me my 5ax cap. So this will be the value of E1n. Okay, so I hope you have understood how to identify the normal component of the electric field. So if this is the normal component of the electric field, so what will be the tangential component? Tangential component can be calculated as E1 vector equals to E1t vector plus E1 n vector. That means E1 vector is nothing but sum of the tangential component and the normal component. So from this equation we can get E1t vector is equals to E1 vector minus E1 n vector. So this E1 vector is nothing but it is my 5ax cap minus 2ay cap plus 3az cap, and this will be again minus 5ax cap E1 n vector, just now we calculated. So my E1t will be nothing but minus 2ay plus 3az cap. Okay, so if E1t is this, then obviously E2t vector will be what? E2t vector will be same, minus 2ay cap plus 3az cap. Then once we have calculated E2t, our next emphasis should be on calculating E2n vector. And in previous example, we have already derived the relation that E2n vector is nothing but it will be E epsilon r1 by epsilon r2 into E1n vector. This epsilon r, it is given as 4 epsilon naught. This is given as 3 epsilon naught, and multiplied by E1 n vector, which is nothing but your 5ax cap. Okay, so epsilon naught will get cancelled out. So what will be left out with is 20 by 3 ax cap. Okay, so this will be my E2n. So finally my E2 vector will be nothing but it will be equals to 20 by 3 ax cap minus 2ay plus 3az. So again we have calculated E2 vector based on the conditions given in the question and based on the expression of E1, which is again given in the question, and by applying the conditions of by applying the boundary conditions for electric field. Okay, so with this we conclude our video on boundary conditions. If you have liked the content, please don't forget to like this video on YouTube, and also if whatever you have, whatever suggestions you have, please feel free to comment it on the YouTube chat box. Okay, so thank you for watching this video.